Okay, I'm here starting some short videos on Chapter 2. In the first video here, we'll talk about reflection and refraction and total internal reflection. So Chapter 2 talks about optics, and I'm assuming in this graduate course that the optics part is all review for you folks, that you've had this in a physics class before. So the first topic is reflection and refraction, and so the very first thing we have to do, we have to understand what a ray of light is. You know, perhaps we've used a laser pointer and we would say we'd like to draw a picture of the light, the laser beam coming out of that laser pointer as a ray. We can think of it as a ray here. What does that really mean? Well, rays are a construct that we use, and the ray itself is perpendicular to a wavefront, and a wavefront is the set of points in space with a constant phase. So you can think of this ray as representing the wavefront of many electromagnetic waves that are all in phase here in this picture. And you can see that they all have the same phase. Maybe they have phase 90 degrees along this line here. And in fact, that's exactly what the ray represents. The ray represents the propagation direction of a light beam, and it is perpendicular to these wave fronts. Okay? So you can think of these black lines as wave fronts, and this red one as the light ray. And so we draw light rays, and I'll draw them as red in these slides here. You can think of light rays and ask how they propagate. Well, the interesting thing is when we have the interface between two media with different refractive indices, N1 and N2. And we will take, in our case, N1 is greater than N2 here for our purposes. And so we're going to assume a planar interface between two media of refractive indices N1 and N2, and we're going to ask ourselves what happens when a ray hits that interface. Well, the first thing I'm going to do is I'm going to say we're going to draw a line perpendicular to that interface, and that will be the normal to the interface. And then I'll characterize the rays by their angles from that normal. And so, for example, I can bring a ray in here, and I can hit this point with my ray, and I can ask, okay, what happens to this ray as it hits this interface? Well, what I'll do is I'll draw that this ray has been refracted, it is bent, but it also is reflected. Okay, so I can ask about these angles here. This I'll call the angle of incidence, theta-1. And the very first rule is that the angle of reflection, theta-1 prime, is equal to the angle of incidence. Okay, so this makes sense. Common phenomenon, I think. We can see good images in reflections. But then the refracted ray, I'll call its angle relative to the normal. I'll call theta-2. So theta-1 is in index N1, theta-2 is in index N2. And the rule that governs this is called Snell's law. I think the French call it Gauss's law, probably more properly. And the rule is that N1 sine theta-1 is equal to N2 sine theta-2. Okay? Where these angles are measured from the normal. And this is Snell's law. Since we have theta being in the range from 0 to 90 degrees, and that implies that the sine is an increasing function and that in turn implies that theta 2 is greater than theta 1 when n1 is greater than n2. And that's how I drew it here. So, in other words, the larger the index, the smaller, the medium with the larger index has the smaller refracted angle. Okay, and so we can also well, so that's the summary of Snell's law. Next, we'll move on to look at total internal reflections and the critical angle, Theta-C. So here we have, again, indices n1 and n2, and we have our normal, and we have now a ray picture where we've got an incident angle, reflected angle, and also a refracted angle. Okay, and now our picture, our ray picture now has arrows on it because there is no ray over in this quadrant, for instance, in this picture. Okay, although there's a lot of symmetry here. Well, the critical angle is defined inside the medium with the larger index, and that's the incident angle at which the refracted angle becomes 90 degrees. You see, this refracted angle is larger than the incident angle, theta 1 here. And if theta 1 keeps increasing, theta 2 stays ahead of it, and eventually theta 2 hits 90 degrees before theta 1 does. And I can draw that schematically here in a series of 4 refractions where the incident angle theta 1 is increasing by steps. So here's sort of the continuation of that ray, and here's the bent ray. As theta 1 increases, instead of going straight, it's bent further. As theta 1 increases further, the bent ray eventually hits 90 degrees, and when that refracted ray hits 90 degrees, then this is the critical angle, this incident angle. So these are the incident angles, theta 1 increasing. And here theta 2 has hit 90 degrees. Okay, and there is actually no refracted ray then. There's no place for it to go. And so we can write that n1 sine theta 1 is equal to n2 sine theta 2, and we can solve for theta 1 in this case. And theta 1 is the arc sine of n2 sine theta 2 over sine theta 1. I'm sorry, over n1. And if theta 2 is 90 degrees, that implies theta 1 is equal to theta critical, which is equal to the arc sine of n2 over n1. It's possible to take that arc sine because n2 is less than n1. Okay, so we can only take the arc sine of a number that is less than 1. And so that works out. So theta 1 greater than theta c implies no refracted ray. And that gives us what we call total internal reflection. Okay, TIR. And in total internal reflection we have no loss. We have a lossless reflection. At least ideally, it's lossless. Imperfections in the surface will cause. So what we can do is we can think of, and remember, this total internal reflection is occurring and is defined, the critical angle is defined in the medium with the larger index. In other words, if you have a piece of glass immersed in air, then the total internal reflection will occur inside the glass. Okay, if this is my critical angle, again measured from the normal, then rays that hit with an incident angle larger than that, that is glancing rays, will undergo TIR, total internal reflection. Okay, for glass-air interface we get, you can just use n is 1.5 for the glass and n is 1 for the air, and we'll get a 42-degree critical angle for total internal reflection. So there's the summary, and thank you.